We will now derive the fundamental formula known as the principle of work and energy. So let's consider the particle shown that has mass m and is subjected to a system of external forces whose resultant is F sub r, which is the summation of all the force vectors. Here's that resultant force. Using a normal tangential coordinate system that we've learned about before, this resultant force has two components, where summation F sub n, the net force in the normal direction, equals the net force times sine theta, or the resultant force times sine theta, and summation F sub t, the net force in the tangential direction, equals the resultant force, or the net force times cosine theta. Applying the scalar equation of motion and the tangential direction to this particle, we have the net force, summation F sub t, equals m a sub t, the particle's mass, times its tangential component of acceleration. From the kinematic equation, a sub t ds equals v dv that we learned about in chapter 12, we can substitute by rearranging that one, a sub t equals v times dv by ds, into the equation of motion. Then we can integrate both sides of this equation, assuming that initially the particle has position s equals s1 and speed v equals v1, and later a position s equals s2 and speed v equals v2. Upon integrating, we obtain the following, where we have summation integral s1 to f2 f sub t ds equals the integral v1 to v2 mv dv. And we get on the right side 1/2 m v sub 2 squared minus 1/2 m v sub 1 squared. Recall that work, as we learned earlier in chapter 14, is calculated as uppercase U sub 1, 2 equals integral s1 to s2 f cosine theta ds, where f cosine theta represents the tangential component of the external force acting on the particle. If we go back into this diagram here to see that the force in the tangential direction is the resultant force, this force here, times cosine theta, which is what we have in this integral here. The normal component of the external force, always acting normal to the tangential axis, does no work on the particle since its direction is always perpendicular to the direction of displacement of the particle. We have therefore derived the principle of work and energy, which is stated here. Summation U sub 1, 2 equals 1/2 m v sub 2 squared minus 1/2 m v sub 1 squared. The term on the left-hand side of this equation represents the total work done, the summation of all the work done by all external forces acting on the particle during the time period t1 to t2. Each term on the right-hand side is of the form 1/2 mv squared, which should look familiar to you. It represents the kinetic energy of the particle. Kinetic energy is a non-negative scalar quantity that measures the energy of the particle as it relates to its motion or its speed. Kinetic energy is denoted by uppercase T. That's the symbol or the letter we'll use throughout this entire class, uppercase T for kinetic energy. Kinetic energy has the same units as work. That would be joules, which is a Newton meter, or foot-pound typically. An equivalent and more concise way to express the principle of work and energy, or PWE, is as follows, just by rearranging this formula here and expressing the kinetic energy as T, where we have T1 plus summation U1, 2 equals T2. Since the principle of work and energy involves analysis of forces and calculations of work done on the particle, a proper and complete free body diagram, FBD, of the particle is required to be drawn before calculating total work done on the particle and before applying and solving the principle of work and energy.